growth and decay. So growth and decay is when we do real world problems. In real world, we generally start with the initial condition. And that's for the initial condition, we're going to use the 0th term, which just stands for U0. So that's, when you see that, that's just the initial value. Now when we do growth or decay, it's a geometric formula, so you see something like this. UN equals U0 times R to the N. Now when we talk about what U0 is, the initial condition, UN is the term, like what we get. Now R is our growth factor, but keep in mind, R is always 1 plus or minus whatever your growth / decay factor is. We'll always start at 100%. Whatever our current value is 100%. So then we just start adding or subtracting from that. So don't make, R should be something adding or subtracting from 100%. That's kind of the key to this whole problem here. And then N is time. So we're going to do our first example here. The initial population of rabbits on a farm was 50. The population increased by 7% each week. How many rabbits were present after 15 weeks? 30 weeks? How long would it take for the population to reach 500? So we're going to do the first part first. So for A, I'm going to write down the formula, right? It's UN equals U0 times R to the N. My initial condition is 50. And then here, this is where the people make a mistake, right? This is not my R. We're increasing by 100%. So we start off at 100%, or 1, and we're adding 7% to that. So it's 1 plus 0.07, or R should be 1.07, right? We started at a normal amount, which is 100%, and then we're adding 7% to that. So my formula should be UN equals 50 times 1.07 to the N, where N's the number of weeks. In our first problem, it's 15 weeks. Now this is the application problem, so we can use a calculator. So for U15, it's going to be 50 times 1.07 to the 15. So 50 times 1.07 to the 15th. And we get 137.95, so approximately 134 rabbits. Now, does that make sense? Well, we start off at 50 rabbits, and we're increasing population by 7% each week. So yeah, 134 is more than 50. It makes sense. Now look what happens if I took out that 1. If we just put it 0.07%. We would have got a tiny number, right? That's scientific notation. That's a negative. So we had a small decimal. That wouldn't make sense. How do we grow our population if we're like decreasing? So very important. You always start at 100% and then either add or subtract. 30 weeks. Do the same thing for 30. Let's plug it in. So I'm gonna go back to here, select my thing, and change that to that. And we're gonna multiply like rabbits, and we get U30 equals 50. 1.07 to the 30, and we get approximately 381 rabbits after 30 weeks. So there we go. How long would it take for population to reach 500? So for this one, for B, right, we want our population, which is this guy, to be 500. So we have 500 equals 50 times 1.07 to the N. Now again, we haven't learned how to do this by hand yet, so we're going to use a calculator. And all I'm going to do is go y1, y2, except from the last problem I did. Now in this case, y1 is 500, and then 50 times 1.07 to the x power. Now again, I got to change my window, so zoom standard first. Right, so zoom standard is not going to get the 500. I got to be able to see 500. So I'm going to stop it early. Let's go. Let's change my window here. My Y max to these 500. I'm going to go 600 because I like to give myself a buffer and see if anything happens in between those times here. So here it comes. Come on. And I'm not nearly far enough on my X. So let's go. I'm going to go 100 again. Oh no, this feels right. So let's see how this one graphs. That's not bad. Again, probably a little overkill, but there's my intersection. So let's find the intersection. Second, calculate intersection. Right there, oh, there it is. Easy to see. enter, 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 and I go at 34.03. So n equals 34.03. So how long would it take? You could say it's going to take about 34 weeks or 35 weeks because you want to round up to reach 500. If you say about 34 weeks, I'll accept that. Technically, you got to wait till you actually hit 500, so I'd say about 35 weeks. There we go. So that was a growth one, right? I probably should increase. Now let's do a decay one. Each year, physicist measures the remaining radioactivity in a sample. She finds that it reduces by 18% each year. There was 1.52 grams of radioactive material after 4 years. Find the initial quantity of the radioactive material. So it's slightly different. So let's see, right? Our general formula is going to be UN equals U0 times R to the N. Now, what is my U0? I don't have it. They didn't tell me what the initial amount was. That's what I actually got to find. They did tell me that this, though. I have my R. Now, keep in mind, right, your R is 1 plus or minus the percentage. In this case, it reduces. So my R is going to be 1 minus 0.18, or 100% minus 18%. So my R here is going to be 0.82. So my formula actually has the R filled in. UN equals U0, 0.82N. Now I want to find what U0 is. Well, I do have 1 point that I know. After 4 years, I get 1.52. So when I plug 4 in for N, I'm going to get 1.52 grams. So let's plug that in. Now, unlike the last time where I just substitute my calculator y1, y2, that still works. I don't need to do in this case. This is just a number. I can just divide both sides by this number here, and it's still going to now get my answer. Right, my variable is not a power, so I just divide it. Use my calculator for that. It is an application problem. We're always allowed to use calculators on application problems. So I'm going to get 1.52 divided by 0.82 to the fourth. When you get U0 is approximately, now again, IB we're going to simplify 3 sig figs. So we're going to say U0, my initial amount is about 3.36. So about 3.36. Next question, how many more years will it take for the amount of radioactive material to reduce to 0.2 grams? So we want to reduce to 0.2 grams. So we want this part to be 0.2 grams. So I'll go back to my general equation. Well, kind of. I know what the U0 is now. So UN is 3.36, 0.82 to the N. And I want this to reduce to 0.02. 0.2, not 0.02, 0.2. And for this one, since my variable is an exponent, we're going to do y1, y2. So on our calculator, y1, let's clear off this we did last time. So 0.2, 3.36 to the 0.82n. Or in our case, x. Now I'm going to go zoom standard because it's a brand new graph, so I like to always reset myself first. I thought I put zoom standard, zoom 6. There we go. Now in this case, it's actually really hard to see where it crosses right there. I might have to go right also. Right, so I have this. I want to move it more to the right because that's where it crosses. And I don't only see so far up. So like my y1 is 0.2. So I could probably go as high as like 1 or 0.5. So I'm going to change my y to that. I'm going to change my x more to the right. So let's go all the way to, I don't know, 30. 30. And then let's make this from 0 to 1. Because that's all I see. All I need to see my y is 0.2. So there's 0.2. And again, I went all the way to 30. I want to see where these two lines cross. And they cross right there. So then I'm going to hit second graph, find the intersection. So that's close. Hit enter a couple of times. Now, I haven't done this earlier, but every time you graph on the calculator, it helps if you draw a picture. It doesn't have to be a perfect picture, just a sketch, so we know, oh, that's where you got your answer from. some side effect, and that is 14.217. So my n here is about 14.217. Now, before I say my answer is like 14, I guess 15 would be right, because I got to round up, because that's when I'm actually going to cross it. So 15. Remember what the question actually asked. How many more years? Look at, they made italicized it for you. More years. So it's 4 years to get to there. So after 4 years, so it's be 15 minus 4, so 11 more years. About 11 more years. There we go.